Assalamualaikum and good morning to all of you. So today we are continue our topics in this chapter 2 with the Coplanar force system. So by now you know already how to construct the free body diagram and draw forces. So for this Coplanar force system you will learn how to do the drawing of free body diagram and also know the forces and do the calculation. So coplanar simply means all the forces lie flat on a 2D surface. So that means the X and Y plane. So any force acting on the particle can be broken down or resolved into its I-axis and J at the y-axis components. For the particle to be in equilibrium, the sum of all forces must be zero. So this will give us two simple equations to work with, which are the sum of forces in the x direction is 0 and the sum of forces in the y direction is 0. So let's look at a very simple example here. So imagine a particle here being pulled to the right with a known force for 10 newtons and an unknown force F here is pulling along the same axis in this figure 3.5. So when we set up our equations, it is crucial to assume a direction for the unknown forces. So this unknown force here. So let's guess that the unknown force F is also pulling to the right in the positive x direction. So then our equation will become the positive F plus the positive 10 Newton equal to 0. So when we solve this equation, we will get the positive F equals to negative 10 Newton. So what does this negative sign mean? So it doesn't mean negative force exists. It just tells us that the arrow direction we originally guessed on our free body diagram was wrong. So the force F actually acts to the left due to this negative sign. So your procedure is simple for this type of example for coplanar force system. So step 1, you need to draw the free body diagram. And step 2, you need to apply the equation of equilibrium, which is the summation of force along x direction equals to 0, and the summation of forces along y-axis or y direction equals to 0. So components are positive if they point along a positive x-axis or a positive axis, and negative if they point along a negative axis. So that's for coplanar force system, the 2D system. So let's look at this example 2.1. So we need to determine the tension in cables BA and BC. So BA and BC that are holding up a 60 kilogram of cylinder. So look at this geometry very carefully. Okay, so first we know the cylinder's weight causes a downward tension in cable BD. So the equation of weight is mass times with gravity. So it will give you 60 kilogram times with the value of gravity, which is 9.81, and the total for this mass times with gravity will give you around 588.6 Newton. All right. So next, what you need to do is you need to isolate ring B to draw our free body diagram. Okay, you isolate the tension at point BD to draw your free body diagram. So we have the tension A pulling up and left, the tension C pulling up at right at a 45-degree angle, and the downward tension of BD, which is 60 times with 8.81, that will give you around 588.6 Newton just now, which is a pulling straight downward. Okay, after isolating that, this is what you get for your free body diagram. You should construct your free body diagram similar to this one. So then we apply equations of equilibrium. For the x-axis, summation of forces along x direction equals to 0. So you need to resolve the tension C and the tension A into horizontal component. So horizontal components mean along the x direction. Same goes for the y-axis. We have the summation for equilibrium, summation of forces along y direction equals to 0. So you need to resolve them vertically. Okay, so and subtract the weight pulling down here. So we can see for x direction, you use the TC here using the trigonometry rules and the small triangle of trigonometry. Okay, same goes for the y direction. You need to refer to the trigonometry rule, okay, and the Pythagoras theorem. So by solving these two equations, the equation 1 and equation 2, simultaneously, you will get that the T A and TC to be, so TC 476 Newton, and the tension at A equals to 420 Newton. Example 2.2 is very similar. Here a crate here which weighs around 550 Newton. So what you need to find is the forces in supporting cables AB and AC. Okay, so the best way of practice is you need to identify what are the given parameters. So what are the given? So the what is given is the box weight around 550 Newton and the geometry as shown here. Okay, and then that's for given. And what you need to find? What you need to find is the forces of the ropes at the center point of A to B and AC. Again, your plan will be step 1, draw the FBD at point A as your center point, and step 2, solve using equations of equilibrium. So looking at the free body diagram on this slide, we have FB, force B pulling up and left at 30 degrees. Force C is pulling up also right at a 3, 4 and 5 slope. And you also have the force D here equals to 550 Newton, the weight which is pulling straight down. So you then can write your X equation, negative FB cosine 30 degree plus FC 4 divided by 5 equal to 0 for the equilibrium equation. So same concept applies to your Y equation. You write as FB sine theta of 30 degree plus force at C 3 divided by 5 minus with the weight equal to 0. So don't neglect the positive and the negative signs. So FB here, because it points towards the opposite direction of x-axis, so which is why you have a negative sign here. So solving the above equations 1 and 2, you will get force at point B equals to 478 Newton and force C equals to 518 Newton. So you can also put the arrow showing the direction of your force at the particular point. So in this case, the force at your point B will direct at this, following this arrow shown here, and for point C, the force will acting up to the right, upward position. So you notice both answers are positive, meaning the directions we assume on the diagram here were absolutely correct. For example 2.3, we have a slightly more complex system. A 20 kg of lamp supported by multiple cords and rings at point C and D. So when you see a problem like this with multiple connection points, don't panic. So you need to know what you need to do. So first, you just draw multiple free body diagrams. So instead of one, you have multiple. So you will start by drawing an FBD at joint D, where the weight of the lamp hangs, and solve for chords from point DE and point DC. So once you know the tension in chord DC, you can draw a second free body diagram at joint C as your center point and use that known force of this DC to find the tensions in cable CA and the force along cable CB. So this is how your free body diagram should look like. So you draw, instead of one, you have two free body diagrams for the same problem. So you start at the center point of D in your first free body diagram to find your unknown forces, and then if you get the forces you need here from DC here, you can draw another free body diagram at the center point of C, since you already know from the calculation from here, you get the new force here, and you can find the forces along the tension of point C to B and point C to A. Okay, so apply the equations of equilibrium along the x and y axis to the free body diagram of joint D shown in figure A. You will get the equations for y-axis and x-axis. Okay, and then using the result of FCD here, which is originally from the first free body diagram that you find, you apply the equation of equilibrium along the x and y axis to the free body diagram of another joint D, okay, shown in figure B. So you have equation 1 equilibrium equals to 0 for the force along x direction, and equation 2 along the y direction. And then you solve equation 1 and 2, that will give you the force of CB equals to 275 Newton and force at point CA equals to 243 Newton. So you can also take a look at the solution video for this example at the YouTube link given here. So now look at the crane holding the electromagnet at the bottom of the slide. So you know the weight of the electromagnet, but you need to know the force in the 3 chains here. 1, 2, 3 chains to ensure is it safe or not. So this system, the whole system, represent the direction of 3D system. So this is not flat, so it's actually in 3D systems. So we welcome to the 3D force systems. In 3D, we resolve forces into I, J, and K components. For the system to be in equilibrium, 3 equations must be satisfied. So it's the same one. Summation of forces along x direction equals to 0 for equilibrium equation. Same goes for the y direction equals to 0. But in 3D, we add one more, which is in the z direction equals to 0. So let's try a 3D problem in this example. We are given the geometry here, like this one, of a particle with known forces of 600 Newton and also 900 Newton acting on it. That is unknown magnitudes that given in the geometry. And what are the unknowns? The unknowns are, we have 3 forces, F1 here, F2 and F3. So given the geometry and 2 forces of known and unknown forces, you have F1, F2 and F3. So you need to find, what are you going to find is the magnitude of forces F1, F2 and F3, the unknowns. So our plan remains exactly the same. Draw the free body diagram, then apply our 3 equilibrium equations. So we sum the forces along the x-axis like this, equation 1, and we do the same for the y-axis followed by the z-axis. So notice now we have 3 equations, 1, 2, 3, which perfectly allows us to solve for our 3 unknowns. So solving the math, we will get the force 3 equals to 776 Newton, F1 equals to 466 Newton, followed by F2 equals to 879 Newton. So example 2.5 here shows 40 lb. So lb here is a common abbreviation for pound. So basically we have a crate of 40 pound shown in figure 312a. This is the geometry. So we have the three cables A, B, A, C and A, D attached to a ring A. So because the cables pull in 3D space, the easiest way to handle this is to express each force in Cartesian vector form. So we find first the coordinates for point B and C and write out the position vectors for each cable. So for instance, FB is expressed using its I, J and K vector components. In FC is expressed the same way, the I, J and K components. For FD, it will point straight along the x-axis, here the x direction. So it's just in the I direction because it's only point straight along the x-axis. And the weight will act straight down here. So it's purely in the negative k direction, which gives you the negative 40k. So once we express all forces as vectors, equilibrium requires that their sum equals to 0. So what you need to do is to group all the vector form terms together. So you need to group all the I terms together, okay, all the j terms together, and all the k items, the k terms together, setting each group to 0, equals 0, equals 0, and equals 0. So you get equation 1, 2, and 3. So solving this system of equations tell us that the force at B and force at C are both 23.6 pound, and force at D you will get 15 pound. So our final example 2.6 follows the exact same logic. So we have a 40 kilogram of flower pot held by the three cables, cable B, C and D. So the weight will act downward at 40 kilogram times with the gravity value 9.81 Newton. So cables A, B and AC lie along the X and Y axis, making them easy to express, no problem. While cable AD goes up at an angle in 3D space. So you need to set up your equations of equilibrium. So a tip here, so it's must to start with the Z axis for this particular problem. So you write down the summation of force along Z direction equals to 0, because the only unknowns pointing in the Z direction here might just be the one cable FAD here and the F and the weight. Okay, so the weight pulling downward, which is 40 times with 9.81. So here solving the summation of force along z direction equals to 0 immediately gives us the force of AD equals to 763 Newton. So using this result, you can substitute it into your x and y equations to find the FAC and FAB. Okay. So one cable and the weight. So you will get the force of AC equals to 392 Newton and force AB at about 523 Newton. So you can also refer to the video solution for this particular example at this given YouTube link here. Okay, so let's wrap up what we have learned in this chapter. So we started by defining equilibrium. The sum of all forces on a particle must equal 0, meaning it stays at rest or moves at a constant velocity. Then we learned that the most critical tool in your statics is the free body diagram. You just need to remember the 3 steps. You need to isolate the particle, draw every active and reactive force, and label your knowns and unknowns. So once your diagram is drawn, the calculation will be straightforward. So for coplanar or 2D problems that we have learned just now, you need to sum the forces in the x and y directions. For 3D problems, you simply add the z direction and need to use Cartesian vectors to keep everything organized. So in your final calculation, if it gives you a negative force, don't worry. It just means the arrow on your diagram is pointing the wrong way. So instead of positive, it will be in the opposite direction when the calculation gives you a negative force. So next time, for the upcoming topics, we will build on this concept and start looking at the equilibrium of rigid bodies where size and shape do matter. So for now, we don't regard for the size and shape, we just consider the mass, right, and the force. So for next topic, for equilibrium of rigid bodies, we consider the size and shape of the particle. So please review the examples that we have covered yesterday and today, and have a more practice setting up your own free body diagrams. Have a great day, and I will see you in our next session. Thank you.